First of all, thanks a lot for the kind invitation. Again, always a pleasure to be here and hear some excellent glycoscience. And I guess also as an introduction to this whole session, you're going to hear a lot of interesting talks this morning. So my idea was, last time I talked a little bit about cylation of antibodies and B-cell extrinsic. We have more data on that one, but that's maybe rather for next year. So today I decided on telling you a little bit about IgG4, because that's kind of very interesting antibody subclass that is out there, and how maybe glycosylation or modulation of glycosylation can be useful to modulate this activity. Now, you all may know that different types, of course, there's different types of subclasses, but especially if we think about antibodies in therapy, they're used, of course, all of you know that, as cytotoxic antibodies to kill or deplete target cells. And here it's largely really the IgG1 antibody that is used, and you can glycoengineer that without fucose to make it bind better to Fc gamma receptor 3A. Now, if we talk about agonistic antibodies, however, and that could be checkpoint control, it could be anti-CD40 antibodies. I'm going to talk about the anti-4-1BB antibodies, the anti-137 antibody. Here, you don't, in many instances, don't want these high binders to Fc gamma receptors for various reasons. We can discuss that. And here, antibodies such as IgG4 and IgG2 really dominate. And these are very special because you can have, for IgG2, different types of disulfide switch variants. This is really Mark Crack's work here. And the IgG4 is generally thought to be an antibody that has a very low kind of capacity to interact with Fc gamma receptors. Now, a little introduction to IgG4. It's a weird antibody. Again, this is known. I mean, you can do many interesting things, or the antibody itself does many interesting things. Itself can do something that is called Fab arm exchange. So in the serum, an IgG4 antibody of two different specificities, they can kind of switch their Fab arms, so the antibody becomes a natural bispecific antibody. And this is kind of important because the antibody then will be functionally monomeric. It will not have two arms with the same specificity cross-linking target antigens, but will have two different arms. And this is why most of the therapeutic IgG4 antibodies, they're actually engineered in their Fc part to prevent that Fab arm exchange. Another very interesting point is, and this is the general notion why companies use IgG4 antibodies if they want to have antibodies that have no effector function, because it's known that IgG4 has a very low binding to Fc gamma receptors and a very low activity, therefore, in ADCC activity, low binding also to the macrophages, phagocytosis activity, low capacity to activate the complement system, and again, it is rarely forming immune complexes, again, because it's functionally a monomeric antibody. So this has been, and IgG4 can also have increased levels of Fab glycosylation, which has been shown in a variety of in vivo IgG4 antibody responses, and again, has all these Fc variants here that make it do these kind of things that are completely different from all the other IgG subclasses. However, and again, this is the reason why companies love to use IgG4 if they want to have antibodies with low effector function. However, it's important to note that IgG4 is not inactive, right? This kind of notion before, as you see it, not doing any ADCC, not binding to Fc receptors, this is just not true. And moreover, you read more and more these days that IgG4 has an increased affinity to inhibitory receptors, so that could actually be an active immunomodulatory antibody. And then typically two papers are cited, Pierre Bruns's paper, and it's kind of weird to find that information in the paper. So I'm just going to show you the figures here. This is IgG4. This is the binding. You probably can read this to all different types of activating Fc gamma receptors expressed on CHO cells or other cell types as a monomer. And as a monomer, IgG4 really can only bind to the high affinity receptor. That was also very interesting, discovered a couple of years ago. So this is binding as a monomer to the high affinity Fc gamma receptor 1. So clearly it's not a non-binding antibody. But of course, in vivo, the relevant situation is immune complexes. So an antibody rarely can act, an IgG antibody, as a monomer. It needs to act as an immune complex. And here, really, it binds to many, many different types of receptors, Fc gamma receptor 1, Fc gamma receptor 3, allelic variants of 3A and 2A, mostly the high affinity variants, very little to Fc gamma receptor 2B. So wherever that information comes from, it's not a preferential binder to Fc gamma receptor 2B. So it is binding as a complex actually quite well to activating Fc gamma receptors. Now we did that, so Pierre did that with a different type of immune complex, just by cross-linking with a secondary antibody. We used the same kind of assay, but generated immune complexes with TNP-BSAs, with a protein, and then did high and low cross-linking with antibodies. And again, an IgG4 antibody, this is binding to cellular Fc gamma receptors. You can see a very nice binding to Fc gamma receptor 3A in the V allele, not in the F allele. So this is very interesting, as it has this allele-specific binding. There is some OK binding to 2B, but also to Fc gamma receptor 2A, again to the H allele, way more than the R allele, and Fc gamma to the high affinity receptor. So it is a binding antibody, but in an allele-specific fashion, right? It's not an inactive antibody. And I think knowing the Fc gamma receptor alleles you're working with in patients or where you inject your antibody becomes important if you really want to delineate how this antibody works. We have also addressed this before I come to the main topic in vivo. So and I'm going to come to that. We're using humanized mice because the issue with many of the new targets that we have is they're human antibodies, and we don't have the mouse antibodies. So we have to study, if we want to assign function to it, we have to study it in vivo, and we do this in humanized mouse models, where we transplant a human immune system at the day of birth into newborn mice. These mice are immunodeficient, and then these mice develop an entire human immune system. And we did an additional trick because, of course, human IgGs can bind to mouse Fc gamma receptors. We created a new mouse strain that lacks all the mouse Fc gamma receptors. So in this system, we really can study the interaction of human antibodies just with human cells and human effector function. So we did 2 assays in this kind of mouse model. We used an IgG4 antibody targeting platelets, and you can see here compared to IgG1, this is a platelet depletion, very good activity, IgG3, very good activity, IgG2 and 4, very low activity in getting rid of platelets. So this would be a very small immune complex, whereas when we target B cells, we can see IgG2 antibodies in vivo platelet depletion do as well as IgG1, and IgG4 also very efficiently depletes the B cells. So it is an antibody that can clearly have ADCC, ADCP effector functions. Another important thing when you read the literature these days, of course, you do BIACOR. I mean, you have to start somewhere, right? And the BIACOR assay, SPR assay, is used very widely to distinguish between a binding antibody. So this is show mouse IgG binding, mouse IgG2A or 2C binding to Fc gamma receptor 1 and 4. In the mice, you see a very nice binding. And this would be the antibody that cannot be glycosylated. You see no binding, right? And so you would say, well, okay, this antibody will have very good effector function. This antibody will have no effector function. It's aglycosylated. It doesn't bind in the BIACOR, so it should not work. And this is actually true. So this one doesn't work, and this one works very well. But what about these guys here? So they behave. So we did also a couple of years back treat antibodies to deglycosylate them either with endoglycosidase S, right? And this leaves, usually all the antibodies are fucosylated. This leaves the fucose residue on here and the N-acetylglucosamine. Then you can do a trick to further get rid of the fucose, so you only have the antibody with the N-acetylglucosamine. And this looks in BIACOR exactly the same as a fully deglycosylated antibody, right? So if you look, so this would be monomeric binding, protein to protein. If you look at these antibodies as an immune complex binding to cells, you can see, yes, PNG is F, basically no more binding to the inhibitory receptor, to Fc gamma receptor 3. There is still binding to Fc gamma receptor 4, and there is still binding to Fc gamma receptor 1, depending on how large you make the immune complex. Now, more interestingly, when you look at in vivo activity, you can see that this antibody has full activity. So this is the Black 6 mice injected with the untreated antibody. This is the one treated with endo-S, and this with endo-S. So this is just the N-acetylglucosamine. It's fully active. This one here is inactive. So just the BioCore does not tell you. It's a good first indication, but without knowing the function of the antibody, you cannot tell this is functionally inactive. This works exactly fine. What you can see is that the antibody, the less sugar you have, the more it depends on the higher affinity receptors. Because the activity to Fc gamma receptor 3 is completely ablated, but you maintain activity here, and this is then, if you look for mice, knockout mice, which Fc receptors are important, it's then the higher affinity receptors if you have less sugar. So the less sugar, the more the antibody depends on the higher affinity Fc gamma receptors. So again, telling you, really, this is a correlate, but you have to look at it for each antibody in vivo for whether this is no activity. All right, but now let's come to IgG4 and what happens if you deglycosylate IgG4. You lose binding to, and this is human now, Fc gamma receptor 3A. The binding is completely abrogated. To B, there's low binding anyways. To A, abrogated binding. You still have about 50% of binding to the high affinity receptor, even if you have a fully deglycosylated variant of IgG4, and that may become important in the next step when we think about how can we modulate antibody activity. But now let's come to the main topic, and this is CD137. So this is 41BB. This is a very promising target as an immunomodulatory antibody because you can give it to the patient and it really rapidly expands T cells. It's very potent in expanding your ongoing T cell response. So the idea, of course, is to have, if you have limited tumor responses, anti-tumor responses, to really boost them and make a lot of these tumor-specific T cells. There's a variety of antibodies targeting the 41BB molecule. The typical thing about these molecules is that they are functionally trimeric. They are cross-linked by the ligand, which is also trimeric, and this then gives you this very strong T cell activation signal. There have been 2 antibody formats that have been in the clinic. Both of them failed because of high toxicity. There's one antibody. This is the Relomab antibody. This is an IgG4 format. As you can see here, it's a superagonist antibody, and it's called here Fc gamma receptor promoted. So people are a little bit unsure. Do you need them? Do you not need them? What's the role of Fc gamma receptors? And there's an IgG2 antibody. Of course, this can bind better to Fc gamma receptors, but it also binds much lower here, this molecule. And this is really Fc gamma receptor dependent. It's an agonistic antibody. Superagonist, kind of independent of anything else, right? But still, that's a nice thing about this review here, Fc gamma receptor promoted. And as you can see here, of course, one could give up on the target, but when you then look what's going on, you see that companies don't want to give up on that target. There has been antibody engineers have found this kind of field, and you have an incredible variant of new antibodies targeting this type of molecule that are out there to kind of make it work, because it's a really, really potent target. So our idea was, well, but if we know their kind of Fc gamma receptors may play a role, despite it's an IgG4 antibody, what can we do with respect to glycosylation? Does it play a role at all? Can we deglycosylate the antibody? Can we, and the most important thing in this field really is, can we separate toxicity from activity, right? That's the holy grail in this kind of field. Because usually you get both. You get a better activating antibody, you get more toxicity. So trying to figure out if that works at all, and the question and the answer really is open to that is really very important to figure that out. All right, so this now brings me to this model system that we are using. So this is a humanized mouse model, NSG mice, so immunodeficient mice, additionally lacking all the mouse activating Fc gamma receptors. At the day of birth, the mouse babies are transplanted with the human immune system. And then in these mice, you have the development of B cells, T cells in the thymus, B cells and T cells in the periphery. You have a very nice B cell development in the bone marrow. You have follicular structures in the spleen and in lymph nodes, and all different types of as I said here, the immature B cell population, but also NK cells and myeloid cells. So this allows us, at least in part, to address the function of all these molecules that are out there, because if you just would use a classical transgenic mouse system, what will happen is that, yes, you have then the human molecule on a mouse cell, but everything else, the signaling below, would be just mouse. And here we just purely look at really the human immune cells reacting to these kind of immunomodulatory antibodies. Okay, first thing is CD137 expression. So we looked in different human organs, bone marrow, thymus, spleen, and blood. And this is what you see in humans, CD137 on T cells. It's expressed to a low level. And during steady state, it's really also an activation marker, so it becomes upregulated upon T cell activation. And the same thing is true in the humanized mice. If we look in different organs, a low level during the steady state. So this seemed fine, so we have no aberrantly crazy expression of this molecule during the steady state. So what about if we give this antibody? Does it work in humanized mice? And this would be a lymph node of a humanized mouse treated with a control antibody in blue here. You can see it's a little bit difficult with the lights, but you can see there's just a light blue staining here. This is the T cells in this lymph node in humanized mice. If you give this antibody, you wait 1 week, the lymph nodes are just exploding. So you get a massive expansion of human T cells in the lymph nodes. You also get the mouse CD68, so the myeloid cells are there. So the whole structure is filled with T cells. Human dendritic cells also present in these kind of lymph nodes. So this antibody really does what it's supposed to do, also with respect to the timing in these humanized mice. Then, of course, so this is the wanted effect. Then what about the unwanted effect? And humans typically have issues with the liver. So you typically, with these kind of antibodies, get liver issues, T cell infiltrations into the liver. And we use 2 different doses. I'm going to come back to that later, why we did that. So a 3 microgram per gram dose, 6 microgram per gram dose, both clinically relevant doses. What you see here is this is the liver, and all of these arrows marking things here, this is not supposed to be there. So this is T cell infiltrates around the portal veins, T cells infiltrating the liver and causing liver inflammation. Interestingly, at the higher dose, 6 microgram per gram, we also see these infiltrations abundantly all across the liver. So this is not, it looks a little bit like a kidney, but it's actually a liver, where you have all these T cell infiltrates, very much around the bile ducts, but also then around the smaller blood vessels. So yes, we see toxicity. So this is also maintained in this mouse model. So really allowing us now to study if we deglycosylate this antibody, does the glycosylation, does this interaction play a role for antibody activity in vivo? This just shows you we deglycosylated this antibody, the CD107 antibody, and as I showed you before, this leads to about 50% reduction of this antibody in binding to cellular Fc gamma receptor 1, so as expected. You don't completely get rid of it, but you clearly reduce it. So what is happening then to the animals? So this just shows you the general effects of this antibody on body weight and body temperature. You can see if you use this, especially this low dose, 3 microgram per gram, where you have this massive infiltrates in the liver, really across the sinusoids and the portal vein. You get after really you can set a timer. Once the antibody starts kicking the T cells off after 7 to 8 days, you get a change in body temperature. The animals feel bad, and this then recovers. With respect, interestingly, if you deglycosylate this antibody, you have much less of that effect. And at the higher dose, you don't have this effect on body temperature and also on body weight. So it seems like really this low dose seems to be more toxic compared to the high dose. And deglycosylation clearly already helps with this kind of severe drop here in body temperature when the T cells kick off. Now, the most important thing is, of course, what is the effect on T cell activation? And T cell activation really is an induction of CD137 expression. And this would be the green and the blue. So the green is always the deglycosylated, and you can see T cell activation actually is not impaired. Actually, in some instances, it's even better if you use the deglycosylated antibody. It's a little bit here at the high dose, a little bit slower, but it still kicks off, and you see a very good and absolutely comparable level of T cell activation, even with the deglycosylated antibody. If we look on the actual expansion of T cells, again, you can see this kind of a very rapid expansion. We see here, this is the blue curve with the normal antibody. Again, if we deglycosylate, we can get an expansion. It's sometimes a little bit slower, but in the end, it always is the same. So we don't get this massive peak here that is really inducing the toxicity, but we get a more mild expansion, which in the end also, but always reaches the same levels as if we keep the antibody completely intact. Now, what about the organs? And this is really another very good advantage of this model system. We are not limited to the blood, but we can actually look in organs. We can look in the thymus, we can look in the spleen, we can look in the bone marrow, we can look in the lymph nodes. And what we see is that this antibody largely acts in the lymph nodes. I showed you this lymph node before, massive expansion of T cells. We can see that if we look at the organs and facts analysis as well. So the major activity of this antibody is not acting on the bone marrow, it's not acting in the thymus. It's very interesting. It's acting in the spleen, but it largely has this activity really in the lymph nodes. So it leads to this massive expansion and proliferation of T cells in the lymph nodes. And again, if we deglycosylate this antibody, we don't see any major change here. So the antibody, despite being deglycosylated, does not lead to an inhibition of T cell proliferation in the lymph nodes. And what I showed you before, this was in the peripheral blood. It's just a little bit slower, but in the end, this confirms this. The deglycosylated antibody does as well. And this is looking here at the T cell subsets, not going to go into details here. So we see the same effects. We see an expansion of cytotoxic T cells mainly, but also of T helper cells. So the same thing, but less side effects. An interesting thing is also that this antibody not only works on T cells, but you get CD137 upregulation also on myeloid cells and NK cells. And here we saw another very interesting phenotype. If we use the deglycosylated antibody, we see a much better activation of monocytes compared to the T cells, and a much stronger and sustained activation of the myeloid cells compared to the usage of the fully glycosylated antibody. So again, you have a change of effector cell specificity targeting different cells to become activated more efficiently. The same thing on NK cells. If you just look here, NK cells usually you don't see much of activation via CD137, a little bit, but again here with the deglycosylated we see a much better and sustained activation of NK cells at different antibody doses. So again, the antibody deglycosylation, especially on the innate immune cells, NK cells, myeloid cells, leads to a faster and more pronounced activation. On the T cells, it leads to a slower but equal activation. So more mild activation, not this immediate peak that you see typically with this antibody. And of course, this immediate peak, the issue that you have is a cytokine, right? This is always known. Anti-CD40 antibody, this antibody, you trigger a cytokine storm. And this makes you feel really, really bad and also causes this kind of tissue damage. Now what we see here, if you use the antibody, again, this is very nice. You see, if you treat with anti-CD137, you get IL-6 in the serum, MCP1, you get interferon gamma. And if you treat the antibody with PNGSF, you can really, at the low dose, also at the high dose, you can not fully abrogate. I think that's important because you want a little bit cytokine, you want activation of T cells, but you can get rid of this peak of IL-6 production. You can slow down MCP1 production, and you can also get a more mild level of interferon gamma. Now, very interestingly, if you use the high dose, and that's known for these type of antibodies, you actually get a lower level of cytokine production. And the point here is, if you activate these trimeric kind of molecules, if you use too much antibody, the antibody no longer cross-links, but it binds as only with one Fab arm, and then this leads not to the cross-linking of the target molecule, but rather a monomeric interaction, and this leads to a lower cytokine level. And this you completely abrogate, at least here in the serum, by using the PNGSF antibody. Still remember, the T cells still become expanded. We get T cell expansion, but we don't get this cytokine storm. So what about pathology? And here we also saw a very interesting phenotype, because when we looked then in the liver at the low dose, where we cannot fully control the cytokine response, we still see this infiltration in the liver of immune cells, which is here still largely around a little bit around the sinusoids, but again, largely around the portal veins. But when we look at the higher dose, where we have this kind of distinct kind of infiltrates, we can completely get rid of them. So at this dose here, where we have limited cytokines, we can completely impair basically the side effects, liver infiltrations. So this really, in a dose-specific effects, allows you to distinguish or separate organ pathology from the immune stimulatory activity of this antibody. Okay, that brings me to the summary and what we probably can do. So the effect of glycosylation on human immunomodulatory antibodies, we can study that in humanized mice, and this is really something that is totally underappreciated in immunomodulatory antibodies, that we can use glycoengineering to vary it, to make them better, to maintain their immune stimulatory activity while preventing their pathology. It leads to a very rapid expansion of T cells in these mice, and the dose impacts the pathology. I think this is all very important to note, that this humanized mouse model recapitulates that, because in classical mouse models you sometimes don't see that. The mouse T cells just respond differentially. And then the deglycosylation, so modulation of glycosylation of this antibody, really leads to a delayed but similar expansion of T cells at both doses, more pronounced activation of myeloid cells, reduced cytokine levels, so less cytokine storm, and a reduction of tissue pathology at the high antibody dose. So really we think that the take-home message here is that immunomodulation, immunomodulatory antibodies, deglycosylation, but also other types of more distinct changes of the sugar moiety may really help to make these antibodies better, and most importantly, create a more bearable therapeutic window for these kind of very potent immunomodulatory drugs. Work was done by Markus Biburger, Michaela Seeling, also Carmen Reitiger working with the humanized mice, and funding by the German Research Foundation and the NIH. Thanks for your attention.